Hey everybody, this is part one of the 3.6 notes where we're going to look at derivatives as rates of change in motion. So we typically refer to these as particle motion questions. Now this is the first section in the chapter 4 part 2 notes. So it's a little confusing because it's 3.6 in the book. But really what we're looking at is applications of derivatives. So we're going to introduce some phrases and what they mean and what to look for. The relationship we need to understand is between position, velocity, acceleration, and speed. So if we look at this, typically we'll refer to the position function as s of t. It doesn't have to be s of t, but typically that's what they use. So we'll look at s of t is the position function. All right. So in terms of that, when we take the first derivative, so s prime of t, that's going to represent the velocity of the function, which can also be v of t. So we can, sometimes velocity will just be referred to as v of t. And if we take the second derivative of s double prime of t, then that's going to be the acceleration function, which is also referred to as a of t. All right, so it kind of says below that if s of t represents the position of a particle along the x-axis at any time t, then v of t is going to be the velocity and a of t is going to be the acceleration. In that context, the following statements are going to be true. So if we have a phrase initially, basically what that means to us is that time is equal to 0. So t is equal to 0, which means that this is the starting position of the particle. At the origin, all right, because we're talking about a particle moving along the x-axis, at the origin means that x is equal to 0. When we refer to the particle being at rest, that means that v of t is equal to 0. So the particle is at rest when the velocity equals 0. Positive velocity. So if we have a velocity that is positive, meaning greater than 0, that tells us that the particle is moving right. So a positive velocity is telling us the particle is moving to the right. And that would mean that a negative velocity, so a v of t value less than 0, would tell us that the particle is moving to the left. All right. If we keep looking, we have the average velocity, okay, or it could also be referred to as the approximation of the velocity over an interval. That is going to be the change in position over change in time. So you want to think of slope, but in this particular case, we're looking specifically at the position function. Okay, so we're going to use the position function to calculate the average velocity. So this could be s of b minus s of a over b minus a. Other ways you could think of this is the same thing as the slope of the secant line for s of t. Whoops, it's not an s. For s of t. Instantaneous velocity at time t equals c. So that the instantaneous velocity, that's where the derivative is going to come into play. So the instantaneous velocity at t equals c is going to be s prime of c, okay? Or we could also think of that as v of c. So that's the velocity at a single moment. Instantaneous acceleration at t equals c, that's going to be s double prime of c. Again, or we can think of a of c, depending on how we name the function, and that's going to be the acceleration. So acceleration at a single moment. All right, so average acceleration, all right, or the approximation of acceleration is going to be represented by the change in velocity over the change in time. All right, which again, we could think of that as v of b minus v of a over b minus a, which is the slope of the secant line. So slope of the secant line for velocity. So one thing you want to make sure you guys understand is if you're finding average velocity, you have to use the position function in your slope formula. If you're trying to approximate or find the average acceleration, then we're going to use the velocity function in our slope formula. So it's important that we understand that. All right, so positive acceleration, that would be when a of t is greater than 0. All right, that basically is going to tell us that the velocity is increasing. So we have an increasing velocity if the acceleration is positive. If the acceleration is negative, so a of t being less than 0, that would then mean that the velocity is decreasing. In order for a particle to change directions, so if you think back to what we said earlier, when there is a positive velocity, the particle moves right. When there's a negative velocity, the particle moves left. So in order for a particle to change directions, v of t must change signs. It would not be enough for v of t to become 0. V of t must change signs. All right. The next two things we're going to talk about is speed. All right, and we talk about speed being increasing and speed being decreasing. Before we can even really talk about that, I want to make sure that we understand that speed is going to be the absolute value of velocity. Okay, so that's the relationship that speed has with velocity and acceleration. In order for speed of a particle to be increasing, v of t and a of t have the same sign. So it doesn't matter if they're both positive or both negative. If velocity at a certain point and acceleration have a certain point at a certain point at the same point have the same sign, meaning they're both positive or they're both negative, that would tell us that speed of the particle is increasing at that moment in time. And speed is going to decrease if v of t and a of t have different signs. So that's what you're going to want to look for if a question talks about is speed increasing or decreasing. You're gonna have to know the sign of both velocity and acceleration at that given point in time. All right, guys, so that's kind of an introduction to some notation and some meanings that you're going to see within these problems. In the next video, we'll start looking at some examples where we're going to apply these ideas. So make sure you guys check out part 2 to continue the notes.